A distance is supposed to be a fact that holds still. A ruler laid across a table gives the same number tomorrow as it gave today. A road sign 40 miles from town still tells the truth later, whether the car moves or not. That is the deal distance makes with us on Earth. Between two galaxies, the deal is broken. Ask an astronomer how far one sits, and the honest answer is not a fixed number, it is a number tied to a moment, because the same question, asked again later, returns a larger one. The first clean evidence came in 1929 from Edwin Hubble. Farther galaxies were receding faster, in proportion, not at random, a relation Georges Lemaître had reasoned his way to a little earlier, which is why it now carries both names. If distance and speed climb together like that, then space itself is stretching, everywhere, in proportion to how much of it already lies between 2 points. Not objects flying through space, but the space between them growing. Follow that ratio far enough, and the gap starts widening faster than light can ever close it. Past that point, nothing sent from here today, at any speed, will arrive. That is the reversal hiding inside an ordinary-looking number. A galaxy's distance is not a secret being withheld. It is incomplete by nature, the way a location is incomplete without the date it was true, and it is unforgiving in one specific way. For almost everything out past a certain distance, waiting is not neutral. It is the one thing guaranteed to make the number worse. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. So, let's begin. Hubble's own data was modest. A couple dozen galaxies, measured with instruments that would look primitive in an observatory today, on a mountain in California, one photographic plate at a time. Each plate took hours of patient exposure to gather enough faint light from a single distant smudge to say anything useful about it at all. What made the result hold up was not its size. It was the shape of the pattern once all those plates were finally laid side by side. Plot distance on one axis and recession speed on the other, and the points do not scatter. They climb together, roughly in a straight line, as if something simple and universal were setting the rule rather than each galaxy doing its own thing for its own reason. A pattern that clean, from data that plain, is usually a sign that the explanation underneath it is also plain. And in this case, it is. Nothing about any single galaxy needs to be unusual. The rule belongs to the space between all of them. This pattern was not something anyone set out looking for, and that is easy to walk past too quickly before the exception arrives. Hubble and the small team working with him were cataloguing galaxies, measuring what could be measured without a prior theory demanding that distance and speed climb together in exact proportion. The pattern emerged from the data itself, uninvited, the way a shape sometimes emerges from a pile of individually unremarkable objects, once enough of them are finally laid out side by side. That is usually the most trustworthy way for a real pattern to be found. Not chased, but noticed. Not every galaxy in the sky obeys it though, and the exception is worth naming early, because it will come back later tonight. Most of what fills an ordinary night sky is close enough, by the standards this account is using, that distance behaves the way it is supposed to. A star overhead sits some enormous number of light years away, and for any practical human purpose, that number simply holds. It does not creep upward while anyone watches, and it needs no date attached to stay honest. The stars making up a familiar constellation tonight will make roughly the same shape a century from now, near enough that near and fixed amount to almost the same thing at that scale. That quiet reliability is not wrong. It is simply local, and it is worth noticing before the account leaves it behind. On a dark, clear night, far from any city glow, without any instrument at all, the sky offers a second galaxy to the naked eye. A faint, elongated smudge, easy to miss, and, once found, strangely steady from one night to the next. Most of what fills the night sky, even to a careful eye, is contained within our own galaxy. It is an entire second galaxy, whole, seen directly, without any telescope standing between the eye and it. That smudge is Andromeda. Unlike almost everything else out there, Andromeda is gravitationally bound to our own galaxy, close enough that gravity, not expansion, decides what it does next. It is approaching us, not fleeing. One of the only galaxies we can see that is doing the opposite of what the pattern predicts. That single exception is not a flaw in the rule. It is what makes the rule easier to trust. A pattern that correctly predicts its own exceptions, instead of quietly ignoring them, is usually describing something real. Nobody traveled to reach this far. A measurement built entirely from ordinary light collected on Earth managed it instead. Nobody traveled to any of the 24 galaxies in that original dataset. Nobody sent an instrument anywhere near them. Every distance, every speed, every conclusion drawn from that data arrived entirely through light that happened to complete its journey here on its own, examined patiently by people who never left the ground. That is worth remembering each time a number in this account starts to feel abstract. Behind every one of them sits actual, physical light, captured and measured, not a theory dreamed up in isolation from anything real. There is one more piece worth holding on to, because it explains how anyone could measure a galaxy's speed from this far away in the first place, without ever leaving home. Light travels as a wave, and a wave has a length. The distance from one crest to the next. Stretch the space light is crossing, and you stretch the wave riding on top of it, the same way a drawn-out spring stretches every coil evenly along its length. A longer wavelength of visible light reads as redder. So a galaxy that is falling behind, left more and more space to cross by the stretching itself, sends light that arrives measurably redder than it left. Not because the galaxy changed color, but because the space it traveled through got longer while it was still on the way. Astronomers call that shift toward red simply redshift, and it is the actual tool behind every distance and speed pair in Hubble's data. Nothing about it requires guessing. A redder than expected line in a spectrum is as countable as a mark on a ruler. The pattern actually looks a little messier up close than a perfectly straight line would suggest. And that honesty matters more than a tidier story would. Individual galaxies do drift a little on their own, tugged by nearby neighbors, wandering slightly off the clean proportional line in either direction. A small, local motion layered on top of the much larger, universal one. That local wandering is exactly why a single galaxy, like Andromeda, can genuinely buck the overall trend at close range, while the pattern still holds firmly once enough galaxies, spread across enough distance, are considered together. A pattern built from real, individually imperfect data that still holds this cleanly at scale tends to be describing something more fundamental than any one galaxy's particular behavior, which is exactly the kind of pattern this account is now going to follow all the way out. Everything else here does not mean a handful of unusual, cherry-picked cases. It means the overwhelming majority of galaxies that have ever been checked against this pattern, across every direction anyone has pointed an instrument, using measurements gathered over the better part of a century by teams with every incentive to find an exception if one existed. Andromeda remains, so far, one of the very few genuine exceptions in reach. Everything else, past a certain distance, keeps to the pattern Hubble found. And the pattern raises an obvious next question, one this account has not answered yet. Exactly how fast is that space growing? Not roughly. Not fast enough to matter eventually. An exact number, in kilometers per second for every unit of distance, the same everywhere, that turns a vague sense of expansion into something you could actually calculate a boundary from. This account has already come a long way using nothing more than an old photographic plate and a straightforward count. A shift in a spectral line checked against 24 galaxies is enough to establish that distance and speed climb together. It is not yet enough to say how quickly. Getting that second piece, the actual rate, not just the shape of the relationship, takes a different kind of evidence entirely, gathered by entirely different instruments, looking in entirely different directions. That is where the account turns next. That number has a name. Astronomers call it the Hubble constant, and it sounds like the kind of thing that should have been pinned down decades ago. It has not been. Two of the best, most carefully checked methods available today, built from completely different kinds of evidence, keep returning two different answers. Neither team has found a mistake in the other's work. The disagreement has a name of its own, and it is where this account turns next, because that unresolved number is not a side detail. It is the one thing standing between the distance is growing and the distance is growing exactly this fast, and here is precisely where it stops mattering whether you wait. The number itself has a plain unit. Once you sit with it for a moment, kilometers per second for every megaparsec of distance already between two galaxies. A megaparsec is just a fixed length, a little over 3 million light years, used because ordinary units would drown the number in zeros. The unit is not the hard part. The hard part is that two of the best methods anyone has for measuring it, built from completely different kinds of evidence, do not agree. This is not the first time the number has needed correcting, and it is worth being honest about that history rather than presenting today's figures as though they had arrived fully formed. Hubble's own original estimate, drawn from that modest 1929 dataset, was considerably higher than either of today's numbers, off by enough that later astronomers spent decades quietly revising it downward, correcting mistakes in how certain kinds of stars had been calibrated, and refining the whole distance measuring chain step by step as better instruments came online. Each correction moved the accepted number, sometimes by a large amount, and each one held until the next generation of evidence moved it again. Today's disagreement is not a break from that pattern. It looks, so far, like a continuation of it, except that this time, for the first time, two independently careful methods are converging on two different, precisely bounded values instead of everyone slowly settling on one. The first method looks backward, almost to the beginning. After the universe cooled enough for light to travel freely, it left behind a faint glow that still fills the whole sky today, stretched by billions of years of expansion into microwaves instead of visible light. That glow is not smooth. It carries a fine pattern of slightly warmer and slightly cooler patches, laid down when the early universe was still dense enough for sound-like ripples to move through it. The temperature difference between the warmest and coolest of those patches is tiny, a few hundred thousandths of a degree, spread across the whole sky, and yet modern instruments map it in enough detail to turn it into an actual measuring tool. The size of those patches, measured precisely, depends on how fast space has been expanding ever since, so the pattern itself becomes a kind of ruler. Read its markings carefully, using the most complete map of that ancient glow yet made, and the expansion rate comes out to about 67.4 kilometers per second per megaparsec. The second method stays close to home and works forward instead. One galaxy at a time. Certain stars, called Cepheids, brighten and dim on a clock so regular that their true brightness can be read directly from their rhythm, the way a light bulb's printed wattage tells you exactly how bright it truly is, regardless of how dim it happens to look from across a large, dark room. Compare that true brightness to how dim the star actually looks from here, and the distance separating the two fall out of the comparison directly. A dimmer than expected star simply has to be farther away by an amount that can be calculated rather than guessed. Exploding stars called Type Ia supernovae do something similar at far greater range, reaching all the way out to galaxies too distant for any single Cepheid to be picked out and measured alone. Chain these together nearby stars calibrating the exploding ones. The exploding ones reaching out past them, rung after rung, like a ladder built one calibrated step at a time, and the same rate can be measured directly without ever touching that ancient glow. Done carefully, with the sharpest instruments available, this method returns about 73.0 kilometers per second per megaparsec. Trusting a number like that, built rung by rung across such enormous distance and time, takes real, checkable work. Every step in the chain, identifying a Cepheid correctly, timing its brightening and dimming precisely, separating its light from everything else, crowding the same patch of sky, calibrating against the next rung up the ladder, carries its own small uncertainty. And those uncertainties compound as the chain extends outward, that the final result still lands within about 1% of itself. After all of that compounding, says something about how carefully each individual link has been checked and rechecked before being trusted to carry the next one. Neither number is a rough guess. Both come with real, tightly checked uncertainty attached, small enough that the two results, on paper, should overlap comfortably if they were measuring the same true value. The kind of small, expected disagreement that normally closes on its own as instruments improve. This one has not closed. If anything, it has grown more solid as both sides have sharpened their tools, which is precisely what makes it interesting rather than ordinary. Both have been measured again and again by different teams using different instruments over more than a decade. The gap between them has not closed. It has a name now. Astronomers call it the Hubble tension, and it means something specific. Either one method has a flaw nobody has found yet, or the universe is doing something slightly stranger than the simplest picture assumes. As of the most recent published work, nobody has settled which. Seen one way, the disagreement is small; seen another, it is enormous. And both are true at once, neither cancelling the other out. 67 versus 73 is not a wild swing. The two numbers sit within about 10% of each other, close enough that a casual glance might not think twice about it, at the precision modern instruments are actually capable of. Though, that gap is enormous. Each method now claims an uncertainty of only about 1 or 2%, meaning the two results, if they were truly measuring the same thing correctly, should agree far more closely than they do. A 10% gap between two 1% precise measurements is not a rounding difference. It is a genuine, glaring contradiction dressed in numbers small enough to look modest at first hearing. It would be easy to treat that disagreement as a technicality, a rounding error for specialists to argue over. It is not. Every distance calculated from this rate, including the one this account is building toward, the exact line past which nothing sent today can ever arrive, shifts a little depending on which of these two numbers turns out to be closer to the truth. A faster rate pulls that line closer. A slower one pushes it back. The disagreement is not a footnote on the reversal from Chapter 1. It is the reason the reversal has a precise edge instead of a vague one. None of that changes the basic shape of the answer, and it is worth resting on that for a moment before going further. Both measurements agree on the part that matters most tonight. The rate is real. It is not zero, and it grows the distance between almost every galaxy we can see. The argument between them is only about exactly how fast. A genuinely open question, still being worked out by careful people who keep checking each other's results rather than simply picking a side. Settling that argument is not this account's job, and it may not be settled for years yet, but it is worth knowing, briefly, what the leading suspects actually are, because nobody knows, undersells how carefully this has been checked. This particular disagreement gets taken far more seriously than an ordinary small discrepancy would. And the reason is plain. Cosmology does not have the luxury of a controlled laboratory, where a suspicious result can simply be tested again under cleaner conditions. Every measurement here is made from one fixed vantage point, using light that finished its journey however many billions of years ago it happens to have left. When two completely different lines of evidence, using completely different physics, keep returning different answers this precisely, it usually means one of two things. Either something subtle is being systematically missed in how one or both measurements are made, or the simple model connecting the early universe to the present one is quietly incomplete in a way nobody has pinned down yet. Both possibilities are worth taking seriously, and working out which one is true is currently one of the most active open questions in the entire field. Neither side of this argument has been idle. Here, briefly, is what each has already ruled out. On the local ladder side, researchers have swapped calibrating stars for entirely different kinds, checked results against galaxies in completely different parts of the sky, and used more than one space telescope to rule out instrument-specific quirks. On the ancient GLOW side, independent teams working with the same underlying data have rebuilt the analysis from scratch, using different statistical methods, and kept arriving at the same lower number. Neither side has found the flaw that would make its own result quietly collapse into agreement with the other. The most boring explanation would be a hidden error, a miscalibrated star, a step in the distance ladder that quietly drifts, a subtle bias in how the ancient GLOW gets read. Teams on both sides have spent years hunting for exactly that, rebuilding each step of their own method from scratch, swapping instruments, checking against completely independent stars and independent patches of sky. The disagreement has survived all of it. That does not rule out an error nobody has thought of yet. In careful science, that possibility never fully closes, but it makes a simple mistake steadily less likely with each year the gap holds. The more interesting suspects involve the universe doing something the simplest model does not expect. An early, temporary nudge to the expansion rate soon after the beginning, before the ancient GLOW was even released, which would shift what that GLOW's pattern implies without touching anything the local, star-by-star method measures, or a slight unevenness in how matter happens to be arranged nearby, a somewhat empty region surrounding our own neighborhood, subtly speeding up the local read without changing the true value everywhere else. Each idea makes its own testable prediction, and each is still being checked against new data as it arrives. None has won yet. What can be settled here, tonight, is something underneath both numbers, something both methods already agree on without saying so out loud. A rate like this only makes sense if space itself, and not the galaxies sitting in it, is the thing actually moving. That distinction between things moving through space and space moving on its own is where the account turns next. There is a simple object worth having in hand for what comes next, even if only in imagination. Take a flat sheet of rubber and glue 2 coins to it, a hand's width apart. Stretch the sheet evenly from every edge, and the coins drift apart, not because either one slid across the rubber, but because the rubber between them got longer, while each coin stayed exactly where it was glued. Neither coin has a velocity relative to its own patch of sheet. Measured against the sheet itself, both are standing still, and yet the distance between them, measured with an ordinary ruler laid across the room, keeps growing the whole time. That is close to the actual picture, once the sheet is replaced by space itself and the coins by galaxies. Each galaxy, for the most part, is not flying through space towards some destination. It sits in its own small patch of space, essentially at rest relative to that patch, the way each coin sat still relative to its patch of rubber. What grows is the amount of space lying between one patch and the next. A galaxy twice as far away has twice as much of that space stretching between it and us. So the distance grows twice as fast, not because it is moving twice as hard, but because there is simply twice as much room between here and there for the stretching to act on. Speed climbing in exact proportion to distance is not a coincidence this picture has to explain away. It is exactly what the picture predicts. Automatically, the moment you accept that space itself is the thing doing the growing. None of this requires our own position to be special in any way, and that turns out to matter more than it first sounds like it should. Stretch the rubber sheet evenly, and a coin glued anywhere on it would see every other coin drifting away in exactly the same pattern. Farther coins retreating faster, nearer ones retreating slower, with no coin able to claim it sits at the true, unmoving center of the stretching. Astronomers take the same idea as a working assumption about the universe at the largest scales. Viewed from any galaxy, At a scale wide enough to average out local clumps and voids, the universe looks roughly the same in every direction, with no special vantage point anywhere. That assumption has a name, the cosmological principle, and it is not a leap of faith so much as a tested expectation. Every wide survey of galaxies taken so far has come back consistent with it. It is also the reason nobody needs to worry about the Milky Way secretly sitting at the one privileged spot in an otherwise ordinary stretching sheet. There is no such spot. Every galaxy, observing from wherever it happens to be, would see essentially this same account playing out, centered on itself. There is a second consequence of taking space itself as the moving part, and it answers a question that tends to surface the moment anyone pictures the rubber sheet stretching in every direction. What is the sheet stretching into? A rubber sheet on a table expands into the room around it. More table, more air, space that was already there waiting to be filled. The universe does not have that luxury of an outside to expand into, at least not one this account, or modern cosmology, has any evidence for. The stretching described here is not space expanding into some larger container. It is the amount of space between any 2 points increasing, on its own terms, without needing anywhere external for that extra space to come from. That is a genuinely strange idea to sit with. Stranger than the rubber sheet fully captures, and honesty requires saying so rather than letting the analogy quietly paper over the gap. The sheet is useful for the relationship between distance and speed. It is not a complete picture of what space itself is doing, and no analogy built from an object embedded in ordinary space ever quite manages to be. None of this needed a name grander than the coins and the sheet to become trustworthy. The strength of a picture like this one is not how dramatic it sounds. It is how many separate, previously puzzling observations it quietly resolves using the same few, simple moving parts without needing a different explanation bolted on for each new case. This is where the redshift from Chapter 1 earns its keep as more than a clever measuring trick. An ordinary object rushing away from you compresses and stretches light the way a passing ambulance changes pitch. A genuine Doppler shift, caused by real motion through the air or through space. What galaxies show instead, past the small, local motions any galaxy has on top of everything else, is a shift that grows steadily and smoothly with distance, matching no single burst of speed, but matching the amount of space the light crossed on its way here. The redder the light, the more room it had to stretch across. That is not the signature of something fleeing. It is the signature of the road itself, lengthening while the traveler stayed still. There is a second, gentler consequence of the same picture, and it is worth pausing on before returning to the harder one. A universe where space itself is doing the moving is not a universe where any galaxy needs to be running from anything, in the way that word usually implies. There is no explosion at some central point, no debris field expanding outward from a blast, no privileged spot. Everything is fleeing. Every galaxy simply sits in its own quiet patch of space, watching every sufficiently distant neighbor recede, while every one of those neighbors watches the same thing happen in reverse. It is a strange kind of universal symmetry. Nobody at the center, nobody truly moving, and yet everyone, everywhere, apparently drifting apart from everyone else at once. There is a real consequence buried in that distinction, worth pausing over before moving on. If galaxies were simply hurtling outward from some ancient push, the way a handful of gravel thrown from a truck spreads out, each piece coasting on the speed it left with, then a galaxy's current speed would depend on how hard it was thrown, not on where it happens to sit right now. Two galaxies thrown at different times, at different speeds, in different directions, would show no clean relationship between distance and speed at all. What Hubble found instead was clean and universal. A coasting gravel universe does not produce that pattern. A stretching space universe produces nothing else. And a stretching space universe makes a very specific prediction that a coasting one cannot. The relationship between distance and speed has no upper limit built in. Push the distance far enough, and the speed implied by that same fixed proportion keeps climbing. Past any number you like, including the speed of light itself. That should sound like a contradiction. It is not. And the reason it is not is the same reason the coins on the rubber sheet never technically moved. Nothing is being asked to travel through space faster than light allows. Space itself is simply providing more room. Faster, the farther out you look. There is a small, satisfying piece of consistency worth noting before leaving this mechanism behind. Every strange result covered so far tonight. Recession, climbing without limit, speeds beyond light with nothing locally broken, an accelerating rather than decelerating universe, all trace back to this same single idea. Space itself, not the thing sitting in it, is the part actually in motion. None of these results needed a separate, unrelated explanation invented just for it. They are all the same physics, viewed from a different distance or a different moment in time, which is a strong sign the underlying picture is the right one rather than a patchwork of coincidences. The everyday intuition this whole account has been quietly overturning is not foolish. It is simply calibrated to the wrong scale. Every distance anyone learns to trust growing up is small enough and close enough that the tiny, constant stretching of space contributes nothing measurable to it at all. A road, a country, even the distance to the moon sits so far below the scale where expansion becomes noticeable that treating those distances as fixed is not a simplification. It is, for every practical purpose, exactly correct. The intuition only breaks where distance becomes large enough, and the objects involved become untethered enough from each other's gravity for a genuinely tiny effect to finally add up to something undeniable. It helps to make that proportion concrete rather than abstract. Go back to the sheet, and suppose stretching it doubles its overall size. 2 coins a hand's width apart end up 2 hands' widths apart. 2 coins that started a full arm's length apart end up 2 arms' lengths apart. The same doubling, applied evenly, produces a bigger absolute change the farther the coins already were from each other. Nothing about the rubber favored the distant pair. It simply had more distance to work with between them. So the same stretch produced a larger gap. Scale that up to the size of the universe, apply it continuously rather than all at once, and the exact proportionality Hubble measured falls out with no extra assumptions required. Redshift itself means something slightly more precise here than Chapter 1 had room to establish. An ordinary Doppler shift, the ambulance changing pitch as it passes, happens because the source and the listener are moving relative to each other through a shared, unchanging space. What stretches a distant galaxy's light is not that kind of motion at all. It is the growth of space itself, happening continuously along the entire path the light travels, adding a little more stretch with every bit of distance crossed rather than applying one fixed shift at the moment of emission. That is why the redshift of a very distant galaxy can be far larger than any ordinary motion could ever produce on its own. It is not measuring how fast something once moved, but how much space has opened up during the whole of light's long journey here. One honest question tends to follow naturally from all of this, and it is worth answering directly rather than letting it sit unresolved. If space itself is stretching everywhere, does that mean everything is expanding? The room, the body in it, the solar system, even the galaxy? It does not. And the reason is a matter of which force is actually in charge at each scale. The stretching of space is real but extremely gentle. A tiny fractional growth spread evenly through every cubic light year. At the scale of a person, a planet, or a solar system, the forces holding matter together. Electromagnetism binding atoms, gravity binding planets to their star, are enormously stronger than that gentle stretch, and simply overpower it without effort. The same is true for an entire galaxy, held together by the combined gravity of everything inside it, and for small, close clusters of galaxies like our own, bound tightly enough that gravity keeps pulling their members back together faster than expansion could ever pull them apart. The stretching only wins, and only becomes visible at all, in the vast, mostly empty space between galaxies that are not gravitationally bound to each other, which is most of them, and which is exactly the space this account has been measuring since Chapter 1. Before naming that boundary directly, it helps to notice what has actually been established so far, because the next step follows from it almost automatically once it is stated plainly. Chapter 3 showed that recession speed is not some separate quantity layered on top of distance. It is distance's own rate of change, produced entirely by the stretching described there, with no independent ceiling written into the underlying relationship. A rule with no built-in ceiling, applied across distances large enough, was always going to reach every possible value eventually, including the very largest one physics recognizes. If the relationship between distance and speed truly has no built-in ceiling, then somewhere out there sits a distance at which the implied speed reaches the one number physics treats as absolute, the speed of light itself. That distance has a name. Astronomers call it the Hubble sphere, and, unlike the fixed distances printed on an ordinary map, its exact size depends directly on the disputed number from Chapter 2. Using the slower of the two measured rates, the sphere's edge sits a little over 14.5 billion light-years away. Using the faster one, it sits closer to 13.5 billion. The true edge, right now, lies somewhere inside that range, roughly 13 to 15 billion light-years away, waiting on the same measurement the last chapter left open. Take a moment with that distance before moving past it. Light leaving that boundary today would need roughly 13 to 15 billion years just to cross the distance, separating it from Earth. If the space between stayed perfectly still the entire time, longer than the age of the Sun, longer than the time since the Milky Way itself first took shape, nothing about the boundary is close, in any ordinary sense of the word. What makes it worth naming precisely, rather than simply gesturing at very far, is not its size. It is what happens to anything trying to close that distance from beyond it, which is where this account turns next. Whichever exact number turns out to be correct, the shape of what happens there is already settled, and it is worth stating plainly before the objection arrives, because the objection arrives quickly for almost everyone hearing this for the first time. A galaxy sitting beyond that distance is, right now, receding from us faster than light travels. Said in those words, it sounds like a violation of one of physics' most carefully tested rules. It is not, and the reason returns to the rubber sheet from a moment ago. Einstein's work actually claimed something more precise than the popular shorthand suggests. Nothing can go faster than light, leaves out the exact scope of that rule, and lets the confusion in. The claim relativity makes, tested now for more than a century without exception, concerns objects moving through space relative to a nearby observer. No rocket, no particle, no signal carried by matter or energy, measured against anything close enough to compare directly, can be pushed past that limit. The theory says nothing at all, one way or another, about how fast the space between two distant points is permitted to grow on its own. That silence is not an oversight. It is the correct scope of a rule built to describe motion within space, applied honestly rather than stretched to cover a completely different kind of question it was never designed to answer. The speed limit built into relativity governs something specific: how fast an object can move through the space immediately around it, measured by someone standing right there next to it. A galaxy beyond the Hubble sphere is not doing that. Measured by an observer riding along with it, that galaxy is at rest, exactly the way each coin sat still relative to its own patch of stretching rubber. Nothing local is exceeding anything. What exceeds the speed of light is a bookkeeping quantity. The rate at which the amount of space between two widely separated points is growing. And that quantity was never covered by the local speed limit in the first place, because it was never a velocity in the sense the limit was built to restrict. Physicists who work with this every day have had to correct this exact misunderstanding among each other for decades. Not only for the public, it is a genuinely easy place to trip, precisely because the word speed gets used for two different things that only happen to share a name. The actual source of the confusion is not a failure of imagination on anyone's part. Ordinary language, built entirely around experiences that happen inside a fixed, unchanging space, has exactly one word for how quickly something covers distance: speed. Physics, once space itself is allowed to change, genuinely needs two different concepts wearing that same single word. The familiar kind, measured locally, bound tightly by relativity's limit, and this second kind, a rate of separation produced by the geometry of the whole universe, which was never a velocity through space to begin with, and so was never a candidate for that limit in the first place. English was not built with this distinction in mind. The physics does not suffer for that. The plain language describing it just has to work a little harder. It helps to notice that this is not the universe finding a loophole in its own rules, the way a technicality might let someone circumvent the spirit of an agreement while honoring its letter. There is no tension here at all, once the scope of each rule is understood correctly. Relativity's limit was always a statement about motion within space. This is a statement about the changing size of space. Two rules governing two genuinely different things do not need to be reconciled with each other, because they were never in conflict to begin with. They only sound like they might be, for as long as the single word speed is left doing the work of both, without anyone pausing to separate them. There is a cleaner way to see why nothing is actually broken. Light passing directly by any observer, anywhere in the universe, at any distance, always measures out at exactly the same speed. That part of relativity has never once failed a test, near a galaxy beyond the Hubble sphere or anywhere else. What changes, out at that range, is not the local speed of light. It is the amount of space light has to cross to get from there to here, and how fast that amount of space is itself growing while the light is still in transit. A runner on a track moving at a constant, ordinary pace is not doing anything unusual. If the track itself is being stretched out ahead of the runner faster than the runner can cover it, the runner still never breaks their own honest, ordinary pace. The track simply grows faster than any pace could keep up with. How confident can this account actually be that the Hubble sphere is real, rather than a mathematical curiosity nobody has confirmed? The relationship it rests on. Recession speed climbing in exact proportion to distance, with no upper limit built into the underlying law, has already been checked, indirectly, across an enormous range of distances, including many galaxies whose implied recession speed sits well beyond the speed of light, using exactly the numbers from Chapter 2. Every one of those measurements remains consistent with the same simple picture. Nothing in the data breaks down, wobbles, or contradicts itself as the implied speed crosses that threshold. The universe simply keeps behaving the way the underlying physics says it should, on both sides of a line that sounds, at first hearing, like it ought to matter enormously, and, physically, does not. Push that picture a step further, because it clarifies something that tends to linger as a nagging doubt otherwise. Nobody standing anywhere along that stretching track ever measures the runner going anything but their normal, honest speed. A second runner planted at any point along the way, however far out, would clock the first runner passing by at exactly the same ordinary pace every time. The discrepancy only ever shows up in the total distance covered, measured from very far away, after accounting for how much extra track has been laid down in the meantime. Locally, everywhere, always, the rules stay exactly as strict as they have ever been. It is only the sum of all that stretching, added up across an enormous distance, that produces a number large enough to outrun light itself. Notice, too, that nothing about this account has needed to bend or soften relativity to make room for it. every prediction relativity makes about local motion, tested now across more than a century of experiments, from particle accelerators to satellite clocks to the bending of starlight itself, continues to hold exactly as precisely as it always has. Everywhere this account has traveled tonight, including at and beyond the Hubble sphere. What changed is not the rule. It is only the recognition that the rule was always narrower in scope than the popular shorthand around it suggested, describing motion through space rather than the changing size of space itself. That image sits right at the edge of tonight's central question. Close enough to name directly, a galaxy beyond the Hubble sphere is already, at this moment, retreating faster than light can close the gap between us. That alone does not yet mean nothing sent there could ever arrive. Speeds like this, tied to a measured rate that itself keeps shifting as better instruments come online, describe a boundary in motion, not a wall bolted in place. Whether that boundary stays put, drifts outward, or drifts inward depends on one more piece of physics this account has not yet earned: whether the expansion rate itself holds steady as time passes or changes. That question turns out to have a genuinely surprising answer, discovered only a few decades ago. And it is where the account turns next. Every boundary named so far tonight came from following the same simple mechanism out to its logical end. This next one comes from a genuine surprise instead, a moment when the universe did not behave the way careful, reasonable physics expected it to. For most of the 20th century, the reasonable expectation was straightforward, and it followed directly from a single, familiar fact: gravity pulls things together. Every galaxy in the universe has mass, and every bit of that mass tugs on every other bit, faintly but constantly, across the whole of space. An expansion set in motion long ago, with nothing new pushing it along, should behave the way a ball thrown upward behaves, coasting outward at first, but steadily losing speed as gravity keeps pulling backward on the whole system. The only real questions in that picture were how much the expansion was slowing down, and whether gravity was strong enough to eventually stop it altogether and pull everything back into a single point. Cosmologists spent decades framing the question as a contest between two plain, physically sensible outcomes. If the universe held enough total mass, gravity would eventually win outright. The expansion would slow, stop, and reverse, pulling every galaxy back together in a mirror image of how it all began. If the universe held too little mass for that, gravity would only ever manage to slow the coasting down, never quite stop it. An expansion that kept thinning out forever, but always losing a little more speed with each passing age, approaching stillness without ever fully arriving there. Both outcomes shared the same basic assumption. Whatever was happening to the expansion rate, it could only ever be slowing down. The only genuine debate was by how much, and which of the two slow, gravity-governed endings the real universe was actually headed toward. That whole framework felt genuinely confident at the time, which is part of what makes the 1998 discovery land as hard as it does. This was not a field guessing wildly at its own future. It was a field that believed, on solid theoretical footing, that it had already narrowed the real universe down to two well-understood possible endings, with the only remaining task being to measure which one applied. Textbooks were written treating the question as fundamentally a matter of totaling up mass. Almost nobody involved in that careful accounting was expecting the ground itself to shift beneath the question being asked. Deciding which of those two futures the real universe was heading toward came down, in principle, to a single measurable quantity: the total amount of mass and energy spread through the universe compared against a specific threshold value that separates enough gravity to eventually reverse the expansion from not quite enough. Astronomers spent years carefully tallying up everything they could account for: the visible stars in every galaxy, the far larger amount of unseen matter needed to explain how galaxies hold together at all, every contribution anyone could measure or infer, The running total kept coming up short of that threshold, suggesting the coast forever, slowing down but never stopping, outcome was the more likely one. Nobody, testing that total, was expecting to find a third possibility that the two-option framing had not even considered. Testing that expectation meant measuring how the expansion rate itself had changed over cosmic history, comparing how fast things were receding a long time ago when their light first left them, against how fast things are receding closer to home, using light that left much more recently. That comparison needs a reliable way to know how far away something extremely distant actually is. And by the 1990s, two independent research teams had converged on the same tool for the job, a specific kind of exploding star called a Type Ia supernova that reliably reaches almost exactly the same true brightness every time it detonates, regardless of which galaxy it happens to occur in. A light source with a known, fixed brightness works like a standardized bulb. However dim it appears from here directly reveals how far away it must be, with no other assumption required. Both teams pointed their instruments at supernovae, far enough away that their light had left billions of years ago, expecting to see faint evidence of that predicted slowdown, distant supernovae appearing slightly brighter than a steady, uniform expansion would predict. Because a decelerating universe would mean less space had opened up between the star and us than a constant rate would suggest. What both teams found instead, independently, using different telescopes and different samples of stars, was the opposite. The distant supernovae looked fainter than a steady expansion predicted, meaning more space, not less, had opened up on the way here. The expansion was not slowing down, it was speeding up, a result that overturns decades of reasonable expectation, earns extra scrutiny before it earns belief. And this one received exactly that. Neither team believed it at first, and the record of their own early skepticism is part of what makes the result trustworthy now. Fainter than expected supernovae can also result from ordinary dust dimming their light on the way here, or from older, more distant stars quietly burning slightly differently than the nearby ones used to calibrate the method. Either effect could, in principle, fake the same signal without any acceleration involved at all. Both groups spent real time trying to explain the result away before accepting it, checking for dust along each line of sight, checking whether older supernovae behaved differently in ways that could be measured and corrected for, testing every mundane explanation available before entertaining the strange one. It survived every check. In 1998 and 1999, the two groups, the High Z Supernova Search Team and the Supernova Cosmology Project, published the same conclusion from independent data, gathered independently, analyzed with independent methods. The universe's expansion is accelerating. The finding was significant enough and confirmed thoroughly enough in the years that followed by entirely separate lines of evidence to earn the 2011 Nobel Prize in Physics. How strange that finding must have felt to the astronomers holding it in their hands for the first time is easy to underestimate now. The strangeness has worn off with familiarity, not with age. Every previous debate in cosmology had been an argument about degree. How much slowing? How much mass? How the story eventually ends. This was a different kind of result entirely. Not a smaller than expected slowdown, but a slowdown that had turned, at some point in the universe's history, into the opposite of itself. Gravity had not stopped pulling. Something else, unaccounted for in every previous model, was now winning against it, and had apparently been winning for billions of years already by the time anyone thought to check. Whatever is driving that acceleration needed a name, since nothing in the previously known inventory of matter and radiation behaves this way. Ordinary matter and its gravity only ever pull inward, never push a whole universe apart faster over time. Physicists settled on a deliberately modest placeholder. Dark energy. The name describes a gap in the accounting, not an explanation. What is well established is its effect, measured now by multiple independent methods that all agree. Whatever it is, it acts like a strange kind of pressure spread evenly through space itself, and unlike gravity's pull, its influence does not shrink as galaxies drift apart. If anything, as more space opens up between things, there is simply more room for that effect to act in, which is part of why the acceleration does not fade with time the way an old, coasting push naturally would. That point inverts an intuition most people carry without ever examining it. Ordinary pushes weaken with distance and time. A thrown ball loses speed, an explosion's force spreads thinner the farther it travels. A wave flattens out the longer it crosses open water. Whatever dark energy is behaves the opposite way, at least in terms of its total effect on the universe. Because it appears to act everywhere, uniformly, per unit of space, and because the total amount of space keeps growing, its combined influence over the whole universe does not fade the way a normal forces would. Gravity is doing the losing here for the first time anyone has measured. Not because gravity got weaker, but because the volume of space for the other effect to act in kept getting larger year after year, tipping a contest that used to belong entirely to gravity. Few results this disruptive move as quickly as this one did from surprising to accepted. Most major revisions in any careful science face years, sometimes decades, of resistance, replication attempts, and argument before the field settles. This one had its central claim independently reproduced by a rival team using different data within roughly a year, and further confirmed by entirely separate lines of evidence not long after, including, eventually, the same cosmic microwave background measurements described back in Chapter 2, which turned out to imply the same accelerating history once analysed with that possibility in mind. Multiple, independent, structurally different kinds of evidence converging on the same strange answer is close to the best confirmation. That has one direct, unavoidable consequence for the boundary from the last chapter. A Hubble sphere set by a constant expansion rate would sit at a fixed distance, neither advancing nor retreating, once and for all. A Hubble sphere set by an accelerating rate cannot behave that way. As the rate itself keeps climbing, the distance at which recession speed reaches the speed of light keeps closing in. Not because anything is moving toward us, but because the threshold itself is drawing nearer, sweeping up more and more previously reachable space as it goes. The boundary explored last chapter was never going to sit still. Acceleration guarantees that it moves, and moving in only one direction, inward, claiming more of the universe with every year that passes. That raises the real question this account has been building towards since Chapter 1, and it finally has enough physics behind it to be answered properly. If the boundary keeps closing in, is there a final, permanent line it settles into? Some absolute edge past which nothing sent today could ever arrive, regardless of how the disputed rate from Chapter 2 eventually gets resolved? There is. It has an exact shape and an exact distance. And finding it is where the account turns next. Everything covered across the last 5 chapters has been building, piece by piece, toward a single honest number, and it is worth marking that plainly before arriving at it. Chapter 1 established that the gap grows. Chapter 2 established, with appropriate honesty, how fast, within a disputed but bounded range. Chapter 3 established why. Space itself, not motion through it. Chapter 4 turned that mechanism into a first real boundary, the point where today's recession already outruns light. Chapter 5 complicated that boundary, with the discovery that the underlying rate is not holding steady, but climbing. Each step was necessary for the one that followed. None of them could have been skipped without leaving a gap in the reasoning that a listener would have had every right to notice. Picture the difference between two kinds of bad news. Because the boundary this account has been circling since Chapter 1 turns out to be the second, harsher kind, not the first. The first kind of bad news is a train pulling away from a platform. Hard to catch once it starts moving, but not truly impossible if you happen to be fast enough, or if the train happened to slow down later. The second kind is a train that is not only pulling away, but pulling away on a track that keeps extending itself faster than any runner could ever gain ground, permanently, for as long as the track keeps being built. The Hubble sphere from 2 chapters ago behaved like the first kind of bad news, a moving threshold, its exact position still tied to a rate under active dispute, closing in as acceleration continues, but never quite pinned down as a fixed, final number. What acceleration guarantees, once it is taken seriously as a permanent feature of the universe rather than a passing phase, is a boundary of the second kind, a true unmoving edge, fixed for all future time, past which nothing. Not light, not any signal, not anything moving at any speed whatsoever will ever arrive here again. There is a natural temptation, on first hearing about the Hubble sphere and this new, stricter boundary in the same conversation, to treat them as 2 versions of the same fact, one just a rougher estimate of the other. It is worth resisting that temptation directly. The Hubble sphere answers a question about right now. Which galaxies, at this exact moment, are already receding faster than light? A galaxy could sit just beyond that line today and still, in principle, end up reachable later, if the expansion rate happened to slow down enough in the meantime for light to eventually catch up. Before 1998, in the older, decelerating picture from the previous chapter, that possibility would have stayed genuinely open. Acceleration is what closes it. Once the expansion rate is confirmed to keep climbing rather than easing, beyond the Hubble sphere today stops being a temporary inconvenience and starts implying something closer to permanent, which is exactly the harder question this chapter is built to answer honestly, rather than only gesturing toward. Astronomers call it the cosmological event horizon, and the name is worth taking apart because both halves of it are doing real work. Event horizon borrows its meaning from the boundary around a black hole, a line past which nothing can send a signal back out, ever, under any circumstance. Cosmological specifies that this particular horizon is not carved out by any single massive object's gravity. It is carved out by the geometry of the whole expanding universe, acting on every point in space equally, with nothing at its center but the observer doing the measuring, which means every galaxy, everywhere, has its own version of this same horizon, centered on itself, and ours is no more special than any other. The reasoning behind its exact distance follows naturally from everything already on the table. Light leaving a distant galaxy right now has to cross the space between here and there, and that space is not standing still. It is stretching at a rate tied to the disputed number from Chapter 2, and stretching faster over time because of the acceleration confirmed in the last chapter. Close enough, and the light eventually wins that race. The space between the light and its destination stops growing fast enough to outrun it, and the light arrives, however many billions of years later, far enough away, and the opposite happens for good. The space between the light and its destination keeps stretching faster than the light can cross it, for every single year that follows, without exception. There is no later moment when the light gets a better chance. The gap that needs closing keeps growing at least as fast as the light closing it, permanently, because the acceleration driving that growth shows no sign of running out. Picture 2 beams of light leaving 2 galaxies at the same moment. One sitting just inside this final boundary, the other just outside it. Both beams start out crossing roughly the same amount of stretching space, at roughly the same rate. The one just inside has a head start that ultimately matters. As billions of years pass, the space still ahead of it keeps shrinking relative to the space it has already crossed, until eventually the beam closes the remaining gap and arrives. However faint and however delayed, the one just outside never gets that advantage. Every year that passes adds more new space ahead of it than the beam manages to cross in that same year, permanently, because the local patch of universe it is leaving is being carried away by acceleration faster than the light escaping it can ever compensate for. Nothing about the two beams differs at the moment they set out. The only thing separating them is which side of the same widening line they happen to start on. Working through that calculation carefully, using the currently accepted picture of how the universe's expansion has behaved and is expected to keep behaving, places that true, permanent edge at a proper distance, measured right now, today, of roughly 16 to 17 billion light-years away. That is a real number, refined over decades by cosmologists correcting each other's early estimates, not a poetic way of saying very far. It sits closer than the 14 or so billion light-year edge of the Hubble sphere might make you expect it to. No. In fact, it sits farther out than that boundary, which makes sense once you remember what each boundary actually measures. The Hubble sphere marks where recession speed matches light speed today using today's expansion rate. While the event horizon accounts for every future year of continued acceleration, which pushes the truly unreachable edge out a little beyond where today's snapshot alone would suggest. One careful qualification belongs here before the consequence gets stated as plainly as it deserves, because precision matters more in this spot than almost anywhere else in this account. The horizon describes light emitted from a galaxy right now, at this present moment, not light that galaxy already sent decades or millennia or eons ago, which may still be crossing space perfectly well and arriving on schedule regardless of where the sending galaxy currently sits relative to the horizon. The boundary is a statement about future communication, not a statement erasing everything already in transit. That distinction will matter more directly a little later in this account. For now, it is enough to hold the horizon as governing tomorrow's light, not yesterday's. Here is the plainest way to say what that number means for a galaxy sitting exactly at it. Tonight, whatever light that galaxy is emitting at this very moment, starlight, any signal, anything at all, will never reach Earth, and no stretch of time changes that. The space between that light and here keeps growing, permanently, at least as fast as the light itself is closing the distance. This is not a claim about our current technology being too limited, or our patience running short. It is a statement about the geometry of the whole universe, applying equally to any observer, using any instrument, at any point in the future. Nothing that could ever be built changes it. That is also, finally, the precise shape of what worse than you think has meant since the opening lines of this account. A distance that simply sits far away, unmoving, is a hard problem. The kind better engines or more patience could, in principle, eventually solve. A distance that is actively, permanently growing past the point where anything could ever cross it is not that kind of problem at all. It is not solved by speed, because no speed is fast enough. It is not solved by waiting, because waiting only widens the gap further. The number itself, roughly 16 to 17 billion light-years, today is not the interesting part. What waiting for it to feel real reveals is that far away and permanently unreachable turn out to be two entirely different claims. And almost everything visible tonight, past a certain point, satisfies the second one, not merely the first. The phrase, roughly 16 to 17 billion light-years, deserves more precision than it has received so far. Where does that range actually come from? It is not a rough guess dressed up in scientific language. It is the direct result of adding up, across all future time, exactly how much the space between here and a given point will keep stretching under the specific rate of acceleration already measured. The same kind of calculation that produced the Hubble sphere in the last chapter, extended forward across every year still to come, rather than frozen at today's snapshot. The range exists because the calculation still inherits the disputed rate from Chapter 2. A slightly faster expansion today implies slightly more accumulated, stretching across all future time, which nudges the final horizon a little farther out. A slightly slower rate today nudges it a little closer in. Once that underlying number is finally pinned down, the range collapses to a single figure. Until then, honesty means carrying the uncertainty forward rather than picking one end of it and presenting it as settled. There is still more to place around that number before the picture is complete. And the next natural question is a spatial one rather than a temporal one. How does this new boundary compare to the edge of everything we can already see? The light that has already arrived, rather than the light that never will. Everything discussed so far tonight has looked outward from a fixed point in space, asking how far something sits and how fast it is receding right now. This chapter turns the same tools toward a different kind of question. Not where the universe's boundaries sit today, but how far its past actually reaches. And the answer to that question turns out to require exactly the same stretching space mechanism already established. Applied in a slightly unfamiliar direction, here is a number that looks like a mistake the first time anyone hears it. The universe is roughly 13.8 billion years old, and yet astronomers routinely talk about seeing all the way out to roughly 46 billion light years. Light travels fast, but it does not travel instantly, and nothing in this account has claimed any shortcut around that limit. So, how can light that has only had 13.8 billion years to travel have covered a distance more than 3 times that many light years? A number that large, attached to an age that much smaller, looks at first like an arithmetic error, slipped past a proofreader. The tempting shortcut is to assume the answer should simply be 13.8 billion light years. 1 year of travel for every year the universe has existed. The same way a car's total distance divides neatly by its total driving time at a steady speed. That shortcut works perfectly well for a universe that is not expanding. It quietly breaks down for one that is, because it assumes the road stayed the same length the entire time the light was on it. The resolution is the same idea this account has been building since Chapter 3, applied to something that already happened, rather than something still in progress. Picture a beam of light leaving a distant galaxy shortly after the universe became transparent enough for light to travel freely at all, heading straight for the patch of space that would, billions of years later, become the location of Earth. At the moment that light set out, the distance between its starting point and its eventual destination was nowhere near 46 billion light years. It was a small fraction of that, because the whole universe was far more compact back then. But the light spent the next 13.8 billion years crossing space that kept stretching underneath it the entire way, exactly the way the rubber sheets stretch beneath the coins in Chapter 3. Each year added a little more travel time, and also a little more expanding room behind the light and ahead of the destination it hadn't reached yet. Add up that stretching across the whole journey, and the distance between the light's starting point and Earth, measured today, comes out to roughly 46 billion light years, even though the light itself only ever traveled at its ordinary, unbroken speed the entire time. Honesty about the limits of confidence matters here too, since precision at this scale is genuinely difficult and deserves to be presented as such. The 6 billion light-year edge depends on a chain of measurements and assumptions stretching all the way back to the earliest moments this account has discussed. The same disputed expansion rate from Chapter 2 among them. Small shifts in that underlying rate nudge the final figure by a meaningful, though not enormous, amount. What stays solid across every reasonable version of the calculation is the basic shape of the answer. An edge measured in tens of billions of light years, several times larger than the universe's age in years, for exactly the reason already given. The precise decimal points are still being refined. The core surprise is not in question. There is a further wrinkle worth including, because it deepens the picture rather than complicating it needlessly. The galaxies whose ancient light makes up that 6 billion light-year edge are not still sitting where that light left them. Billions of years of continued expansion have carried them much farther away since, even farther than the distance their old light traveled to get here. Some of the very earliest sources contributing to that boundary have likely, by now, been carried out past the permanent horizon from Chapter 6 entirely. meaning the account is receiving light from a place that, if a new signal were sent this instant, could no longer send anything back at all. The observable universe is not a map of where things currently are. It is a map of where light used to be able to reach us from, layered with billions of years of change that has continued, invisibly, ever since. That gives this account three distinct boundaries, measured from Earth, and they are easy to blur together into one vague sense of far unless they get separated clearly on purpose. The Hubble sphere, from Chapter 4, marks the distance at which a galaxy's recession speed matches the speed of light today, using today's still disputed expansion rate, roughly 13 to 15 billion light-years out. And it shifts a little as that rate itself changes. The cosmological event horizon, from Chapter 6, marks something stricter and permanent. The distance beyond which light emitted right now will never reach us, no matter how much future time is allowed, roughly 16 to 17 billion light-years out, fixed by the whole future of accelerating expansion rather than by today's snapshot alone. And the edge of the observable universe, the number just worked out here, marks something different again. Not a boundary in the future at all, but the outer edge of the past, the farthest distance any light has already traveled to reach us, over the whole history of the universe so far, at roughly 46 billion light-years. Picture all three the way a stone dropped into still water produces rings spreading outward at different rates, each ring meaning something different about the water's history. An inner ring, a middle ring, and an outer ring, none of them interchangeable, none of them measuring the same moment. Except here, none of the rings are actually moving outward from Earth, the way ripples move outward from a splash. Each one is a boundary calculated from here, at rest relative to us, in the sense that matters, describing a different relationship between here and everywhere else. What recedes faster than light today, what will ever be able to reach us again, and what has already reached us across the whole span of cosmic history so far. It helps to hold all three as a set of nested shells around Earth, rather than three separate facts competing for attention. The Hubble sphere is the innermost shell, and it deals with the present, which galaxies are, right now, at this exact moment, already receding faster than light. The event horizon is the next shell out, and it deals with the future, which galaxies will ever, at any point across all remaining time, be able to send us anything again. The edge of the observable universe is the outermost shell by far, and it deals entirely with the past, how far the earliest light in the universe managed to travel before it reached us, across the whole history of everything. None of the three shells describes the same thing as either of the others, and none of them can be swapped in for the others without changing what the sentence actually claims. There is a further piece of texture worth adding here, because it changes how the earliest observable light should actually be pictured, and the honest picture is stranger and more beautiful than a simple point of light far away. The most distant light reaching us tonight was not emitted by anything resembling a galaxy at all. It comes from a much earlier stage, when the universe was a hot, glowing, nearly uniform fog before stars or galaxies had finished forming out of it. The same ancient glow from Chapter 2, arriving now not as a pattern of temperature ripples, but as the literal outermost wall of everything that can ever be seen. Past that wall lies an earlier universe still, one no light could ever have carried a picture of, because light itself could not yet travel freely through it. The 4-6 billion light-year edge is not simply the farthest galaxy. It is the edge of visibility itself, drawn by the moment light first became possible at all. That separation resolves something that might otherwise nag at the edges of this account. If the observable universe already reaches 46 billion light-years, and the truly permanent horizon sits at only 16 or 17, does that mean most of what we can already see is already lost to us? Cut off? Unreachable? Gone? In one narrow sense, yes. And it is worth saying plainly rather than softening it. The vast majority of galaxies within our observable reach sit well beyond the permanent horizon, meaning any signal we sent toward them today would never arrive, and any new light they emit today will never reach us either. But the light that already traveled here from them, over the billions of years since the early universe, has already made it. That journey is complete. That information already arrived. And nothing about the horizon erases it after the fact. The horizon governs what can still be exchanged from this moment forward. It has no power at all over what already crossed the distance in the deep past. Back when the universe itself was smaller and that same journey was shorter. One concrete image is worth holding onto through all of this. More than 3 abstract numbers competing for attention. Imagine standing at the center of a set of nested circles drawn on the ground, the innermost marking today's already outrunning light boundary. A middle one marking the true point of no return for anything sent from this moment forward, and a much larger outer one marking the farthest edge that any messenger from the deep past has ever managed to reach. Nothing about standing at the center makes this spot special. Every galaxy draws the same 3 circles around itself, sized slightly differently depending on its own vantage point, each one equally valid, each one telling the same 3-part story about a universe with a past, a present, and a future that no longer perfectly overlap. That distinction, complete and unreachable, being different from complete and reachable, is a spatial map of everything this account has been building. What remains is to follow it forward in time rather than outward in distance. Not where these boundaries sit tonight, but what an accelerating horizon does to the night sky, as the years and then the eons continue to pass. There is a natural point, arriving here, to ask what all of this has actually been for. Why an account built to help someone sleep would spend so long establishing a boundary that, by its own account, touches nothing in daily life. The honest answer is that the boundary was never the point on its own. It is the specific, earned shape of an answer to a question this account opened with and has not abandoned since. Is the distance between galaxies worse than it sounds, and precisely how? Everything from here forward follows that same boundary out to its furthest honest consequence. Because stopping short of it would leave the title's own question only half answered. Everything so far has described a snapshot. The universe as it happens to be measured tonight, with its boundaries placed where the current evidence puts them. None of those boundaries are actually frozen. The event horizon from Chapter 6 is fixed only in the sense that its position, calculated from here, does not depend on which galaxy happens to be crossing it. It is not fixed in the sense of staying at the same distance forever. As acceleration continues, doing exactly what the 1998 discovery showed it doing, that horizon does not sit still. It contracts, sweeping up more and more of what is currently reachable and reclassifying it as permanently out of reach. Notice what is actually doing the work in that sentence, and what is not. The closing in is not caused by galaxies fleeing faster in any dramatic new way, and it is not caused by the horizon itself reaching out and grabbing anything. It is simple arithmetic, repeated patiently across enormous stretches of time. An accelerating rate applied to a fixed geometry produces a boundary that creeps inward, year after year, exactly as reliably as compound interest grows, a balance left untouched. Nothing sudden needs to happen for the total effect to eventually become large. It only needs enough time, and accelerating expansion is not short on that. Follow that closing in far enough into the future, using nothing more exotic than the same accelerating expansion already confirmed by 2 independent teams and multiple decades of follow-up observation, and a specific, calculable milestone appears. Given roughly 100 billion more years. A genuinely enormous span. Something like 7 times the current age of the universe, but a finite, ordinary number, rather than an unimaginable one. Essentially every galaxy that lies outside our own small, gravitationally bound neighborhood will have been carried across that horizon, not destroyed, not moved in any dramatic sense, simply placed permanently beyond the point where any future signal could ever cross the gap in either direction. A figure like 100 billion years can sound like a number pulled from thin air rather than one earned through actual work. So it helps to see how it actually gets calculated. The calculation follows the same shape as everything already covered tonight. Take the currently measured acceleration, apply it forward using the same equations that correctly predicted the Hubble sphere and the event horizon, and track how the horizon's distance changes year over year as that acceleration compounds. Run that tracking forward long enough, and the moment arrives when a given galaxy's current distance finally exceeds the ever-shrinking reach of the horizon. Nothing about the method changes between predicting next year's boundary and predicting 100 billion years out. Only the span of time being multiplied through does. Not every galaxy shares that fate, and the exception deserves naming before the number above starts to feel lonelier than it should. Our own small, gravitationally bound neighborhood deserves a clear definition here, spelled out in full rather than left as a comforting phrase. This account named the one nearby exception back in Chapter 1. Andromeda, close enough and moving on the right path to stay gravitationally bound to the Milky Way, regardless of how the wider expansion behaves. A handful of smaller galaxies gravitationally tied to this immediate neighborhood, together usually called the local group, share that same protection. Whatever the expansion does to the rest of the universe, the local group is held together by gravity strong enough, at close enough range, to simply not participate. 100 billion years from now, in this picture, that small, bound cluster remains intact. Whatever else has happened to everything beyond it. The phrase, essentially every galaxy outside the local group, is not claiming what it might sound like it claims, and a sweeping phrase like that deserves the distinction. It is not a claim that every single galaxy everywhere shares an identical fate at an identical moment. Closer galaxies, and galaxies with slightly different local motions, cross the horizon at slightly different times, spread across a wide span rather than all at once. It is a claim about the overwhelming trend, the direction every unbound galaxy is headed in, converging on the same outcome over a long enough stretch of time, even though the exact schedule differs case by case. The shape of the ending is uniform. The timing, in its details, is not. What happens to everything beyond it deserves a plain, unhurried description, because permanently causally cut off can sound more dramatic, stated abstractly, than the actual physical picture warrants. Nothing violent occurs at the moment any given galaxy crosses that horizon. There is no flash, no visible boundary sweeping across the sky, no instant at which anything looks different from one night to the next. The crossing is defined entirely by what becomes impossible afterward, not by anything that becomes visible in the moment itself. From that point on, no signal sent from here could ever reach that galaxy, and no signal it sends could ever reach here. Two regions of the same universe, once in causal contact, quietly and permanently stop being able to speak to each other without either one doing anything differently at all. A sky watched patiently across that whole span would not look like a countdown. It would look, for almost the entire stretch, like an ordinary night sky, continuing to do what it has always done. The same broad bands of light, the same familiar scatter of distant galaxies, thinning only very gradually, year over year, in a way no single lifetime could ever notice. The disappearance this account has been describing is a bookkeeping fact, tracked by anyone doing the physics carefully, long before it would ever announce itself to an ordinary observer glancing upward. Nothing about looking up on any single night, at any point across most of that span, would reveal that the count of reachable galaxies was quietly, patiently shrinking. It is worth placing this figure alongside a few others already earned tonight. because comparison is often the clearest way to feel a number's actual size rather than just hear it. 100 billion years is roughly 7 times the current age of the universe. It is longer than the total remaining lifespan of the Sun, repeated many times over. The Sun itself will exhaust its usable fuel and swell into a much larger, cooler star, long, long before this account's horizon finishes its work. Every star visible in tonight's sky, without exception, will have lived out its entire existence, from formation to eventual fading, well before the number in this paragraph is reached. That is the kind of span being discussed. Not a future within reach of anything currently burning, but one that outlasts it comfortably, several times over. This is a genuinely calculable outcome of ordinary physics, not speculation dressed up as science, and it deserves the same honesty about its limits that every other number in this account has received. The 100 billion year figure rests on a specific assumption that whatever dark energy actually is, its effect keeps behaving the way it has behaved in every measurement taken so far, holding roughly steady rather than strengthening, weakening, or reversing over the vast stretch of time involved. That assumption currently matches every observation available. It is not, and cannot yet be, a certainty about something so far in the future. Cosmologists say so explicitly when publishing results like this one, and this account inherits that same honesty rather than smoothing it away for a tidier ending. If dark energy's behavior changes in some way not yet detected, the timeline shifts. The basic shape of the story, acceleration eventually isolating any gravitationally bound island from everything beyond it, does not depend on getting that one detail exactly right. The word essentially is carrying real weight in that claim, and precision matters more here than a satisfying round number does. This is a statement about the overwhelming majority of the universe's galaxies, following from a mechanism confirmed by every check thrown at it so far, not a claim that every last exception has been hunted down and ruled out for all future time. Science built this account's whole method. State the strongest claim the current evidence actually supports, flag where that evidence runs out, and let tomorrow's better instruments narrow the remaining uncertainty rather than pretending it away tonight. There is a way to sit with a number like 100 billion years without letting it curdle into dread. And it is worth taking, because that is not what this account is for. Nothing alive tonight, nothing that will ever be built by anyone reading this, nothing even remotely close to human timescales is touched by it in any practical sense. It describes a horizon so distant in time that comparing it to a single lifetime or a civilization's entire history barely produces a meaningful ratio at all. What it offers instead is something quieter, a genuine, checkable answer to a question that sounds unanswerable. What happens eventually out past everything we can presently reach, arrived at not by guessing, but by following the same physics that explained a stretched spectral line on an old photographic plate all the way out to its logical, patient conclusion. One loose thread remains before that conclusion can rest easily. And it is a fair question to ask before moving on. Does crossing that horizon mean a galaxy simply disappears from the sky at that moment, the way a lamp goes dark when it is switched off? It does not, and the actual answer is stranger, gentler, and slower than that, which is exactly where the account turns next. The two-boundary picture from Chapter 7 gains one more dimension here, because the future adds something that picture did not yet need. The event horizon marked a line in space, fixed at a given moment, describing what could ever be reached going forward. Add the passage of deep time to that same picture, and the horizon does not just sit there waiting. The boundary in a given galaxy are, in effect, converging from two directions at once. The galaxy drifts outward under ordinary expansion, while the line itself contracts under acceleration, meeting somewhere in between on a schedule neither one controls alone. Nothing about any individual galaxy changes to cause this. The line itself is what moves, redrawing which galaxies belong to still reachable and which belong to already lost. Crossing the horizon and disappearing from view are two different events, separated by an enormous stretch of time, and conflating them is the single easiest way to get this story wrong. Being carried past the horizon only means that no new signal can ever again pass between here and there. It says nothing at all about the light that Galaxy already sent before that moment. Light already on its way, already crossing space, already partway through a journey that started long before the crossing happened. That older light does not simply vanish the instant the horizon closes behind it. It keeps traveling. It keeps arriving. And, exactly like every other signal described so far tonight, it keeps getting stretched by the space it is still crossing, growing redder and fainter with each passing age. This two-stage picture matters for a reason beyond simply being a more careful correction. A sky that instantly went dark at the moment of causal separation would be a strange, discontinuous universe. Unlike anything else this account has described tonight, every other process covered so far has unfolded gradually, governed by the same smooth, patient mathematics. A sky that instead keeps its already departed neighbours visible for a vastly longer stretch, fading them out slowly rather than switching them off, fits the same unhurried character as everything that came before it. The universe, across this whole account, has not once behaved abruptly. There is no reason to expect it would start now. That stretching does not stop at red. Pushed far enough, redshift carries visible light down past red into infrared, then further down into wavelengths no eye, and eventually no plausible instrument could ever recover. The galaxy does not blink out. It fades, the way a sound fades with distance, rather than the way a switch turns off, continuously, gradually, growing dimmer and redder, for as long as there is still light left in transit, to grow dimmer and redder. Each successive wave of light the galaxy sent, moments before it crossed the horizon, has slightly farther to travel through slightly faster stretching space than the wave sent just before it, so the fading does not even proceed at a constant rate. It slows down, growing gentler and gentler, the way an object falling toward a black hole appears, from far away to freeze rather than vanish, hanging on the edge of visibility for a stretch of time far longer than the crossing itself took. Working through how long that fading actually takes, the answer dwarfs the 100 billion year horizon crossing figure from the last chapter by an enormous margin, something on the order of 1 trillion years or more. A span of time comparable to the expected lifetime of the longest-lived stars in the universe. Small, dim, red stars that burn their fuel so slowly they are expected to still be shining long after every star, like the sun has gone dark. The qualification raised back in Chapter 6 becomes important right here. Rather than staying a passing technicality, the horizon governs new signals sent from this moment forward. It says nothing about light already in transit before a galaxy crossed it. A galaxy that crossed the horizon 1 billion years ago has spent that entire 1 billion years still sending us its old light from before the crossing, patiently redshifting the whole way, meaning the sky at any given moment is not neatly divided into still connected and already gone. It is populated by galaxies at every stage of an extremely long goodbye, some barely past the crossing and still bright, some deep into the redshift and nearly imperceptible, with no visible line separating one group from the other. Notice quietly how far this account has travelled to arrive at a distinction this careful. The very first chapters spent real effort separating far away from actively growing farther. This one spends the same effort separating permanently cut off from already gone. Neither distinction was optional, padding along the way. Both are the actual difference between a story told loosely and a story told honestly. And honesty has been the quieter promise underneath this whole account since its very first line. So the honest picture has two separate stages, not one. First, Causal separation. A galaxy is carried past the event horizon, and from that moment forward, nothing new can ever be exchanged between here and there again. A change with no visible signature at all at the moment it happens. Second, and vastly later, true fading. The last of that galaxy's already emitted light finally redshifts past any possibility of detection, closing out a slow dimming that had been underway the entire time since the crossing. The first stage is a statement about the future. The second is a statement about the present slowly running out. They happen roughly 10 to 100 times further apart in time than the crossing, and today are apart from each other right now. 1 trillion years is easy to say and hard to actually hold, so it helps to picture roughly where it sits relative to everything else in this account. The universe so far has existed for about 13.8 billion years. 1 trillion years is more than 70 times that entire span. Not 70% longer, but 70 times the whole age of everything covered tonight, repeated over and over, before the last of a single crossed galaxy's light finally redshifts past detection. Held next to a span that size, the 100 billion year horizon crossing figure from the last chapter looks almost immediate by comparison. Even though it is itself a number, no human timescale comes remotely close to touching. There is one more layer here, belonging to the same honest tradition this account has tried to keep since Chapter 1. The paper responsible for working out this timeline in careful detail makes a further point that follows naturally from everything already covered, worth stating plainly rather than left implied. The same slow fading that eventually removes any single galaxy from view would, given enough time, remove the evidence for the very story told across this whole account: the ancient glow from Chapter 2, the red-shifting galaxies from Chapter 1, the entire observational trail that let anyone piece together an expanding, accelerating universe in the first place. All of that evidence is itself just more light, crossing more stretching space, subject to the exact same fate as everything else described tonight. Far enough into the deep future, a civilization arising fresh, with no older records to consult, would find a much quieter sky than the one visible now, and would have a genuinely harder time discovering any of this on their own. There is a gentle question underneath all of this. What does it mean for anything that might still be out there listening? If intelligent life exists anywhere among the galaxies destined to cross this account's horizon, a civilization arising late enough in cosmic history would eventually lose the ability to detect any of the others. Not through any catastrophe befalling them, but simply because the sky around them would have quietly, gradually emptied of everything beyond their own small, bound neighborhood, the same way this account's own sky is described as eventually emptying. That is not a claim this account can make with any confidence about whether such life exists at all. It is only a note that whatever the answer to that older, separate question turns out to be, this is not, notably, the first time this account has met a limit to what evidence can reach. The event horizon in Chapter 6 set a boundary on where a signal could ever travel to. The observable universe's edge, in Chapter 7, set a boundary on how far back in time any signal has already managed to arrive from. This is a third kind of limit entirely, not spatial and not really temporal in the same sense, but a limit on how long any given piece of evidence stays legible before it fades past the threshold of being usable at all. Every account of the universe, including this one, is built entirely out of evidence that happened to survive long enough and arrive early enough for someone here to notice it and make sense of it. That was never guaranteed. It simply happened to be true for now. That is not a cause for alarm, and turning it into one would be a disservice to how far off it sits and how little it touches anything that matters at ordinary human scale. It is, if anything, a reason for a certain quiet gratitude about the moment happening to exist right now. A universe still young enough, still busy enough, still full of enough visible evidence that a question this large could be asked, and this specific, and answered this honestly, at all. Most of the universe's own history, stretched out across the unimaginable spans still ahead of it, will not have that same privilege. This kind of ending does not resemble the kind most stories reach for. There is no final experiment left to run that would settle everything at once. No single number still missing that would tie off every loose thread this account has left open. The Hubble tension from Chapter 2 remains genuinely unresolved. The exact reach of the horizon from Chapter 6 will keep narrowing as that tension eventually gets settled, one way or the other. What closes here is not the science. It is simply tonight's account of it, a complete, honest pass through everything currently known, offered whole, with its remaining uncertainties named rather than hidden, rather than smoothed into a false sense of a story fully finished. None of that changes anything about tonight, here, close to home. Nothing out past the horizon owes this room an explanation before sleep can come, and nothing about the not knowing left standing needs solving before morning, which is exactly where this account belongs as it starts to settle. Nearly everything covered tonight belongs to almost every other galaxy. Not to this one. The retreat, the widening gap, the horizon closing in, the slow fade stretched across 1 trillion years. All of it describes the vast majority of galaxies. The ones with no gravitational tie to our own, free to drift with the expansion because nothing is holding them back. It does not describe the small, bound neighborhood this account keeps returning to. Gravity, at close enough range, simply wins, tonight and for as long as anyone has any reasonable basis to project forward. That was true in Chapter 1. It has not stopped being true across everything that followed. The whole arc deserves one brief walk back now that every piece is in place. Not to repeat it, but to see how far it actually travelled. It began with a plain observation, a shifted line, a pattern that would not sit still, a broken deal about what distance is supposed to mean. It grounded that observation in a real, if disputed, number, 2 careful measurements of exactly how fast the gap grows, still disagreeing after a decade of honest, independent checking. It built the physical picture underneath that number. Not objects fleeing through space, but space itself lengthening everywhere at once, and used that picture to find a first real boundary, the Hubble sphere, where today's recession speed already outruns light. It complicated that boundary with the one finding nobody expected, an accelerating universe, driving that boundary to close in rather than hold still. And it followed the acceleration all the way to its 2 honest, hard-earned conclusions. An exact, permanent horizon roughly 16 to 17 billion light-years away, and a slow, centuries-spanning fade waiting on the far side of it for anything that crosses. Every step earned the next one. Nothing was assumed at the start that had to be walked back later. Andromeda earned its place in this account as the one visible exception, and it deserves one more honest update before the account closes, because the story of that exception turns out to be its own small, quiet lesson in how real science actually behaves. For years, the working assumption was that Andromeda and the Milky Way were headed for an eventual, fairly likely merger, close enough gravitationally, moving nearly head-on, with early calculations putting good odds on an eventual collision several billion years from now. More recent work, folding in the gravity of a large companion galaxy that earlier calculations had left out, found something more measured, something closer to a coin flip than a near certainty, once every galaxy tugging on the system gets properly accounted for. That is not a story about scientists getting something wrong. It is a story about scientists doing exactly what they are supposed to do, adding one more piece of real evidence, and letting the answer move to wherever that evidence actually points, rather than defending an older number out of habit. What actually changed here, and what did not, matters more for how it happened than for which specific number moved. The earlier calculation was not sloppy. It used the best available measurement of Andromeda's motion, combined with the best available accounting of which Galaxy's gravity mattered to that motion, and it produced an honest, careful answer given what was known at the time. What changed was the completeness of the accounting. A large, nearby companion, Galaxy's gravitational pull, left out of the earlier version not through carelessness, but because its full effect had not yet been worked out, turned out to matter enough to shift the odds meaningfully once it was properly included. That is what a correction driven by real evidence looks like from the inside. Not an admission of failure, but the ordinary, expected texture of a field that keeps looking. There is something worth resting on in that small correction, and it applies to everything else covered tonight as much as it applies to Andromeda specifically. The number for the Hubble constant in Chapter 2, the exact reach of the horizon in Chapter 6, the far future timeline in Chapters 8 and 9. None of these are handed down as unquestionable facts, sealed shut and never revisited. Every one of them is a current best answer, held by people who keep checking their own work, who publish their uncertainty alongside their result rather than hiding it, and who are willing to move the number when better evidence arrives. That is not a weakness in the story told across this account. It is the reason any of it can be trusted at all. A sky that can be checked, and that keeps being checked, is a far steadier thing to rest a mind on than a sky simply declared certain and left alone. A simpler, tidier account could never have offered the particular kind of comfort available here, and it deserves naming directly before this one closes. A story that promised certainty about every number, a single unchallenged Hubble constant, a single exact merger date for Andromeda, a universe with no open questions left in it. Would have been easier to deliver and easier to half remember tomorrow. It would also have been a story about a universe already fully solved, with nothing left for anyone to keep checking. What actually happened tonight was smaller and steadier than that. A genuine boundary, earned honestly, sitting right beside genuine uncertainty, admitted plainly, with neither one erasing the other. That combination, a real answer, held loosely enough to keep improving, tends to wear better over time than false confidence ever does. Return, for a moment, to where this account actually began. Not the galaxies, not the horizon, not even Andromeda, but the plainer claim underneath all of it. A ruler on a table, a road sign 40 miles from town, the ordinary, everyday deal that a distance measured once stays true later. That deal was never really broken, not even for Galaxies. It was simply revealed to be a special case. The case that happens to hold, almost perfectly, for anything small enough and close enough that gravity, not expansion, gets to decide what happens next. A ruler on a table qualifies. A road sign 40 miles away qualifies. So, it turns out, does this entire small, bound neighborhood of galaxies, drifting together through a much larger universe that plays by a different rule almost everywhere else. There is a particular kind of belonging worth naming here. One this account has been building toward without quite stating it outright until now. Belonging is usually described in terms of closeness, the people nearby, the walls around a room, the familiar weight of a blanket. Tonight's account offers a stranger, larger version of the same idea. This small, gravitationally bound corner of the universe is not simply a place sitting inside a much larger, indifferent expanse. It is a place the larger expanse has, in a real sense, left alone, held together, protected from the general retreat by the same ordinary gravity that keeps a body settled against a mattress. Belonging here does not require ignoring the vastness outside it. It only requires noticing that the vastness for this one small pocket of space has already made an exception. That is where tonight's account settles, and it is worth letting the room itself settle along with it. Whatever is actually happening billions of light years out past the edge of what will ever be reachable again Nothing about it reaches into this room tonight. The walls are not stretching. The distance between one side of the bed and the other is not quietly growing while anyone lies still in it. Gravity is exactly as reliable here, right now, as it has ever been, holding the body to the mattress, holding the room to the ground, holding this whole small, familiar corner of the universe together, while almost everything else keeps drifting apart, slowly, patiently, on a scale too vast to ever actually touch anyone lying quietly in the dark. Let the shoulders drop a little further into whatever is holding them up. Let the jaw unclench, the forehead soften, the small tensions carried in without being noticed loosen one at a time, the way a held breath finally lets go once there is nothing left it needs to be ready for. None of what this account described was ever asking anything of a body lying still in the dark. It was only ever asking to be understood, once, clearly, so it could stop quietly nagging at the edge of attention. And it has been. There was a question this account carried from its very first lines, and it deserves to be answered directly, one last time. Now that everything else has been said, is the distance between galaxies actually worse than it first sounded? It is not because the number itself is unusually large, but because the number was never finished, and most of what tonight covered was simply what unfinished turns out to mean in practice. Worse, specifically, in this way, waiting does not help. Speed does not help, past a certain point, no matter how much of it could ever be mustered. The only thing that helps at all is understanding exactly where that point sits, and exactly why crossing it changes nothing about tonight, here, in this one small, gravitationally stubborn corner of everything. Let the breath slow along with it, in through the nose, unhurried, held for a moment, and released. Not because anything demands it, but because there is nowhere else this needs to go tonight. The weight of the body against the mattress is the same weight it has always been. The dark of the room is the same dark it was an hour ago. Somewhere outside, past the ceiling, past the roof, past the last thin layer of air, the sky is doing exactly what this account described, stretching quietly everywhere, at a rate still being patiently measured by careful people, most of them asleep by now too. None of it is asking anything of the body lying here. It never was. Let the account close the way it opened, with something plain, held still, and true. A ruler on a table, a road sign down the road, a room that stays exactly the size it was an hour ago, and will stay that size tomorrow. Out past all of that, unimaginably far, the universe keeps doing what it does, unbothered by whether anyone is awake to watch it. None of that needs solving before sleep can come. It only needed naming, clearly, once, so the not knowing could rest instead of nag. Rest easy. The dark outside the window is doing exactly what it has always done, at exactly the pace it has always done it, and none of it is asking anything more of the body settling into stillness here. Somewhere past the window, past the roof, past the last thin edge of air, the dark keeps doing what it has always quietly done, asking nothing of the room, or the body, or the slow, settling breath inside it. Whatever tonight's account got right, and whatever it will need to quietly revise later, none of it changes the weight of the blanket, the give of the mattress, or the familiar dark of this one small room. The universe will still be here when you wake up. So will we. Good night.